Hi, my name is Samuel and we are from Group 49. Our project is M101 Montage Image Processing. In this presentation, we will demonstrate how a distributed system platform can be used to efficiently process large-scale scientific image data using the M101 Montage workflow as our main case. For this project, we focus on image processing workflows such as becoming more challenging due to the rapid growth of image resolution and data volume. So, image processing typically involves multiple computation stages such as image transformation, filtering, and feature extraction. When large datasets are involved, these stages places heavy demands on CPU, memory, and storage. Running such workflows on a single machine quickly becomes inefficient, leading to long execution times and performance bottlenecks. However, many image processing tasks can be executed independently, such as processing multiple images at the same time. Because of this natural parallelism, image processing is well suited for distributed system. In goal of our project to build a distributed system processing platform on AWS that improve performance and resources utilization. So, to address the challenges, we implemented distributed platforms using a master worker architecture on AWS. Our platform consists of main three components, which is HD Condor, DACman, and Cluster FS. HD Condor is used as the task scheduling system responsible for distributing images processes job across available worker nodes. DACman works on top of HD Condor, define workflow dependencies, ensuring tasks are executed in the correct order, while Cluster FS is used to distributed file system to provide shared access to image data across all of the nodes in the system. So in our platform, HD Condor and DACman manage computational while Cluster FS manage sharing data. DACman represents the image processing workflow as directed acyclic graph DAG, where each of the tasks is only executed once its dependencies are satisfied. This ensures correct execution for steps such as image projection and background correction. HD Condor then schedules these tasks across multiple worker nodes, allowing independent tasks to run parallel and significantly reducing total time costs. At the same time, Cluster FS provides a shared storage layer, allowing all nodes to access the same image and files without duplication. Together, these components from the scalable and efficient distributed platform that is well suited for computational heavy workloads like the M101 montage pipeline.
This project, we are focusing on an example of a workflow processing astronomical images using the M101 montage image processing tool. And it will help us demonstrate how the montage toolkit helps astronomers create a seamless composite mosaic from many overlapping photographs of celestial objects taken at different times by different telescopes. This process involves obtaining images that are in the vicinity of the area of interest, aligning them to a common reference frame, also known as registering, correcting for any differences in brightness between the two images, and then combining the aligned photographs into one high quality composite image. The completed composite image can then be used for various scientific analyses, including investigating the structure of galaxies and determining rates of star formation. This workflow requires the use of a directed acyclic graph or DAG to determine dependencies between tasks. Certain processes must produce output to enable processing of input from other processes. For example, background modeling cannot be conducted on an image until the image has been projected and rendered into its final form. The DAG clearly illustrates all the different types of tasks that can occur at any given time, as well as which tasks must complete before starting any dependent processing tasks. There are some challenges that are involved with this workflow, such as computation and data volume. That's why the montage workflow requires the use of HD Condor to support parallel execution capabilities. Certain tasks like reprojection of separate input images that do not depend on one another and can be performed simultaneously without disrupting each other. Furthermore, the workflow requires frequent access to the same files from each of the computing nodes. This requires the use of a distributed file system. If there were no shared file system, each node would need its own copy of the data, which is an inefficient and inconsistent use of storage space. As can be seen from these two images, the contrast between them visually demonstrates the workflow complexity and the significance of coordinating processing. Specifically, the first image contains poorly combined output that appears blurry and disconnected, while the second image is an accurate mosaic that clearly represents scientific meaning. In summary, the use of HD Condor for scheduling, Dyckman to manage workflow dependencies, and cluster for distributed file access permits efficient performance of the execution of many simultaneous operations. These enhancements will improve system throughput and provide flexible and scalable architecture that can support the continued use of data-driven research for many other heavy workflows.
So now let's talk about our sequence workflow. So the first one will be the input fixed image, because as you can see the first command will be image table, because we need to have a meta table to let us store our input first so that we can continue our next process. So next process will be the reprojection. At this moment the image will be reproject one by one because based on our coordinate system. So the next one will be generate generate the mosaic, and then after generating it will straight away to output the uncorrected image first, because at this moment we haven't do the background correction. So after we output the uncorrected, so that the next one will be doing the overlapping and doing the difference calculation, so that we could able to do the background modeling, so that we can to make the background to be corrected and then to do the overlapping to the image. So after we doing the background modeling, then we will straight away to output the corrected, the final will be correct to be output the corrected mosaic image to the files. So this is our sequence flow. So let's take a look at the next one. So the next one will be our parallel workflow. So at this moment it will become uh, more faster. Uh, so the first one still the same. We still need to input the the image table, fits image. Yes. And then continue will be doing the reprojection for the image. So the next one will be quite different, because at this moment the system will be running two different jobs. The first one will be the generate mosaic at the left hand side, so as you can see, and then the right hand side will be doing the overlapping still at the same time. And then after we generate the mosaic, it will still straight away output the corrected mosaic for us to take a look what's the differences of the background is uncorrected of the mosaic. And then at the same time we are doing the different calculation, so that we could able to continue to do our background modeling, and then we could straight away to do the output of the corrected mosaic. So that's all for our workflow.
Hello, sir. My name is Chao Sheng, and I'm in charge of the demonstration part for our presentation. And now I'll be demonstrating how we can run the M101 Mosaic tutorial using the Deckman workflow running in both parallel and sequential execution modes to see their difference in terms of performance. So now what we have over here is total 12 submission file and 2 Deckman file representing parallel and sequential. So for the submission file, it is to specify all the execution details for each job. And for Deckman file, it is to define the dependencies between jobs and also to ensure a correct execution order. So now I'll start by running the workflow in the parallel execution modes, where in these modes, all the independent jobs can be run at the same time across multiple execution hosts to improve the performance as well as to reduce the processing time. So we'll insert this command to submit the workflow. So now we submit it, and it shows that we have submitted to cluster 355F, and we can insert this command to see what's happening. So over here we can see that the machine with IP14 have claimed the jobs, meaning that it's running now. And at this point, we can see both the machine have claimed the jobs, meaning that here is where the independent jobs, they're running in both different machines, where one machine is processing the uncorrected feeds, where another's one is processing the corrected feeds. Over here, we can see 3 of the machine is in an unclaimed state, meaning that the process has been done. And we can go this mode to see the results. And now by using this WinSCP, we can drag out the uncorrected JPG and corrected JPG to see what is the results. And this is the corrected JPG, whereas this is the uncorrected JPG. So after demonstrating the workflow in parallel execution modes, we'll be running the workflow in sequential execution modes to see what was their difference. So for sequential execution modes, all the jobs must wait for its dependencies to finish before starting. So it can ensure a strict execution orders, but it will also takes more time for processing. So we'll submit using the same command, and here it shows submitted. And it's the same process as the sequential workflow, so I'll just skip this part to see the results. The final outcome of the parallel workflow and the sequential workflow will be the same, but the only difference is the processing duration time. On the left-hand side, we have our parallel workflow. We can see the duration time takes around 126 seconds, where on the right-hand side is our sequential workflows. The duration takes around 157 seconds. So the difference between them is around 31 seconds difference. So we can see, although it's not a huge improvement, but there is an improvement of applying the parallel workflows. And that's all from me. Next, I'll pass to Chumpin to conclude our presentations.
I'm Chumpin, so I'll be talking about the challenges and solution. The first challenges will be the HD control job stuck in idle. The solution will be we check all the other file and we found the error is the path dislocation, so we use the absolute path to prevent it. The next challenges will be we found that when the workflow split into two branches, the job will all queue in the single machine. How do we solve it is we found that our insert is quite big, we have two CPU slots, so we set the request CPUs equals to 2 for each submission file to make the single machine one taking two jobs in the same time. The third is we found that some of the directories we don't have the writable access, so the process might fail. The solution is we change their permission using change one and change on, so all the directories are writable. In conclusion, this project demonstrates how distributed system can significantly improve the performance for data-intensive image processing. By using HDCondo, DACman, and Cluster SS, we have successfully implemented the M101 montage workflow. And this project also provides valuable hands-on experience in configuring distributed system, handling the real-world issues, and understanding the importance of parallelism. This project also highlighted the importance of coordination and resource utilization in scientific workflows. And that's all from us. Thank you very much.